First of all, I just want to say thanks to Travis and everyone at PyData for inviting me to speak again. I've always learned a lot at this conference when I first started coming to it, so I'm very happy to be able to hopefully say a few things that somebody else might find interesting and useful. If you could give me a cutoff time, like a 5-minute cutoff time, somebody could wave. Cool, thank you. So, sort of following the last talk, I suppose in some ways I'm going to talk about when and why not to use a cluster. Despite the fact that I certainly work a lot with distributed systems, there are certain problems that that I work on where I think that sort of a large distributive infrastructure approach is really too big of a hammer, too big of a tool for the job. And the philosophy is to just think about, writing better code, profiling a code, and solving the problem with as simple a solution as possible, as simple a tool as possible. And one type of problem I end up working quite a bit on is sort of in the world of text processing and natural language processing. I mean, it's a big world, and I'm just going to sort of give you a few examples of the types of things that I do on a weekly basis, and sort of why I've started thinking about these problems from this angle. So sort of here's a brief outline. I don't think we'll get through all of it, but we'll certainly get through 1, 2, and 3. And they're sort of the outline essentially speaks of itself, and the problems you end up solving, the problems you solve everywhere. The limited memory problem, trying to make things actually faster and appropriate, and then sort of working with other ecosystems that you need to work on outside of the Python ecosystem. So, introduction. So a couple of the things that I work on quite a bit. I run a team at Columbia which is tasked with building a full-stack digital archive. Sort of rethinking the way that people interact with large collections of documents. In this particular case, it's large collections of historical documents which have been released by the government either through a declassification or through a FOIA procedure. And essentially you have historians and journalists and political scientists who are interested about learning what's in there and being able to do research. So you end up building, I've ended up pretty much building the entire sort of data structuring, backend, API, the UI, I didn't write that, and all the sort of statistical analysis tools which allow for people to interact with this information intelligently. A lot of other stuff I do quite regularly. I work a lot in the law sector, and sort of lawyers quite a while ago figured out that they're essentially overwhelmed in terms of the numbers of documents they have to deal with, right? But once again, like if we think about the volume here, we're not talking about large data volumes, right? But this is not web volumes, this is not Google, these are not the problems we think about when we think about Hadoop or large distributed systems. But these are simply problems where we're dealing with 10 million documents or 5 million documents, and the structure, and it's more of a structural problem than a data volume problem. But nonetheless, you still have to think about memory, right? Because you need to be able to work with these things quickly and produce results. I also think quite a bit about sort of the human-computer interaction side with respect to textual information, right? Your interaction with your email, people's interactions with, personally stored information, also with archival information as well. So been developing a lot of semantic filtering tools and document management tools as well. So, what ends up happening? Well, a lot of time what ends up happening is that your data comes in some sort of a format. If you're very, very lucky, it'll come in some raw XML format. Even if you're exceptionally lucky, it will never be a consistent format. There'll always be issues with it, right? So you end up writing quite a bit of parsers, quite a number of parsers, which are computationally intensive, so that you can take something that looks like this, which is more or less nice, and be able to have something like this, which is a return of some API call, which you can actually use, or a user interface can use, or some developers can use to, figure out what's happening in this collection. If you're unlucky, it doesn't look like this. It looks just like a blob of text, and you end up writing the parsers to deal with that, right? So, what kind of questions do people end up asking so that's not too abstract? People want to look at network interaction questions. So here's an example from the Columbia project. It's a very simple plot of just how many times Kissinger was, sending telcons, having these telephone conversations at any given time. And people really like this stuff because these spikes actually are informative. Some of these spikes are like the, Six-Day War. Some of them, they correspond to historical events, right? So these are just very, very simple tools that a lot of times lead to kind of nice anomaly detection or nice tools for humans to be able to start interacting with a large collection and finding things that are in there. But all of these things require you to have started with raw text. For example, this Kissinger collection is a bunch of raw text, and be able to parse out dates, right? To be able to parse out the body of the thing, to be able to parse out the metadata, and so on and so on. And that's a processing task, right? And you want to be able to do that in an intelligent, quick format, right? This is before any data analysis is really done or any statistics. On the statistical side of things, I do quite a bit of semantic modeling or topic modeling or LDA or LSI or any of these latent semantic models to sort of either look for document similarities or look for document structure to be able to inform people what's happening. So here's some State Department cables and some probabilities of topics and associated words of cables coming from different embassies, right? So these are just examples, but in order for all of this to happen, a large process happens beforehand, right? You start with a large disk of raw text, and you end up something that answers API calls and you're able to do this sort of statistical processing. Also, a lot of classification tasks I'm sure you've seen require feature extraction, right? So here's a classic example. You have a lot of emails. You have some legal case. You're trying to figure out whether these emails are relevant to the case or not relevant to the case. You have some criteria of relevance. You end up running some large feature extraction task, which eventually gets fed into some classification task, which eventually spits out your answer, right? There's metadata extraction. There's sort of feature extraction of different types. So I'm sure you've seen some of these things. And these are the types of things I do every day. So just sort of to sum up, so a lot of structuring, a lot of information extraction, named entity recognition, geotagging, person name disambiguation, text cleaning, extraction, then all the machine learning, the classification, LDA, sentiment analysis, rec systems, anomaly detection, and so on and so on. And these things can range from the simplistic of, once it's structured, plot, some time series, to the more complicated, do some LDA analysis, build an LDA model, use that to create some sort of a system that will allow you to explore the collection. Does that make sense? Okay, so that's sort of a flow that I end up working with quite a bit, right? Start with raw, end up somewhere where it's not raw. Cool. So, what's so hard about text processing in general? Well, in the end, it is quite a bit of information, right? You can't just fit a large collection of text into memory, right? So you can't even fit a large feature set coming from text into memory, generally speaking. So you have to think about sparse data structures. It's language, right? Language it's humanly created language, right? It has its own peculiarities that you need to think about. The structure of the data that you get in its original format is never the same from collection to collection. It's almost never the same within each collection, so you have to deal with that. So you have to think about how to convert that to something machine readable. Sometimes you get things that are, image files and OCR'd and things like that. And sort of a lot of the tools that we have, that I've seen and I've used and sort of developed in industry, have really been developed for solving large data problems, right? And this is not a large data problem, right? This is just a particular type of data problem, which, in my opinion, doesn't require a large distributive solution. It can be solved really on your laptop or on a slightly bigger machine or a couple of machines, as long as you think about it. As long as you really think about the code and really think about how you're implementing it. And essentially, the things that I find fun about text processing are more or less exactly the things that I find hard about it, right? It's kind of an open box how you solve a lot of these problems. Like, what should a digital archive look like right now, right? What of, the original, go to the library and do archival research, or go to the basement of the cloisters and do archival research philosophy translates to the space we're in today, right? That's an interesting human-computer interaction problem, as well as all the sort of other things I end up working on. Okay, so how do I think about dealing with limited memory? Well, I think about it by getting a nice machine without spending too much money, right? Machines are pretty cheap. There's AWS, there's DigitalOcean. They have amazing SSDs on their machines, right? They're incredibly cheap as far as I'm concerned. Sort of we all know these things, I think, by now. And thinking about, just think about, how much actually these things take, right? So if you think about how much text, text sitting on disk, how much is it going to take in memory? If you just try to load it all up into memory, well, it's going to end up taking as much or potentially more space. And so that immediately makes you think about different types of hashing algorithms, different types of data types that you might want to apply to this problem, right? Which we'll see in a little bit. Think about memory quite a bit, right? So we do quite a bit of monitoring, right? So here's Ian. So here's this Ian Langmore. This is a screenshot from his because HTOP doesn't work on my Mac. That's a caveat, right? HTOP tends to give incorrect results on Macs. If you guys didn't know that, just double check before you believe it. I actually don't know why. I don't know if anyone knows why, but it tends to give totally random results as far as what's actually happening. But sort of everything we do, everything we develop, we spend a lot of time monitoring memory and thinking about that, but not from a distributive system standpoint, more just from how to make it work on one machine and make it work quickly. And then we stream, right? So this is text. The one thing that's really nice about text is that it's essentially independent, right? The next item on the list is more or less independent from the previous item, right? And what you're generally doing is you're extracting this information, right? Once you're extracting this information, you're extracting it one entity at a time. You cache that information, whether you cache it in a sparse format, whether you write it to disk, and so on and so on. You can think of these things independently. So you can either think of the lines of text as independent, right? Or you can think of the actual, let's say, files in this case. So we spend everything we do and everything that's in the Rosetta library is essentially just streaming. Stream, optimize the stream, and apply some sort of memory optimized functions to that stream, right? So here's a couple of simple examples, like just streaming by line. Here's a little utility function that crawls some directories, gets all the paths, and opens up those files, and you do something to those files one at a time, right? And so here's a sort of a Rosetta example. So there's a text file streamer class, which takes a base directory. It takes a tokenizer. If you guys know what a tokenizer is, it's something that splits up text into tokens. The simplistic example is basic words, maybe stems, maybe it's lemmatized, maybe it's sentences, whatever your tokens might be. And essentially, just in very, very simple two-line construct, you get an iterator function, and you can just iterate over that, right? So you go for item in my stream, and you have this info stream, which sort of wraps up all the information you care about. You can get the actual text itself, you can get the tokens, you can also get a whole bunch of other information that's sort of coming along from disk, right? Do the same thing from a database. So we have database streamers, both MySQL and Mongo. So essentially you set up your stream by running some query. There's very few constraints on the query. It basically says one of the columns should be named text. That's basically what it asks for. And then you say, okay, do the same thing, stream one sort of row at a time and potentially cache some results. So in this case, I had asked for text, I had asked for the document ID, and I had asked for date. And to make sure that I don't have to go back and get the document ID and the date, I can just cache them along the way. And so these classes allow you to do that, right? Does that make sense? Right, so very simple stuff. So, and if you can combine sort of the above process, like a very simplistic streaming process with some sort of an online learning algorithm, right? You can essentially have a system that is pretty much infinitely scalable and easy to update, right? So you can stream your text as it comes in. You can update your learning algorithm as well, right? So you have these two things that you can control pretty much independently, and you're not bound to having everything at the same time, right? You can just keep learning, keep moving on, right? So those are the two things, right? So stream on the processing side, on the text processing side, and then stream on the statistical machine learning side as well, right? Where the stream here is some sort of an online algorithm. Cool. So what's the summary there? So monitor memory, stream everything, think about caching what you need along the way, right? So you don't have to pass over twice. And when you're talking about huge feature set, well, either use sparse data structures or just reduce the number of features. And there's plenty of statistical techniques to do that. So how do you make things faster? How do we try to make things faster? Well, once again, we don't do anything that I suppose anyone who develops doesn't do. We just think about how long these things take, right? And the nice thing about Python is that it allows you to profile and time and sort of understand exactly what's happening in your code in a multitude of different ways, all of which are useful in their own right. So here's a trivial example from, say, the email feature extraction process above. So you got some people who are trying to steal some money and or something along the way, and we'd like to just tokenize this text so later on we can extract some of these features and tokens and do some classification, right? So here's a simple task. What we're going to do, we have some stop words, we have some punctuation, we're going to split on the comma, we're going to potentially get rid of all the punctuation, and so on, right? This is a very standard technique. So what's the first thing you might write? You might write a very, very simple sort of tokenization function, which might look like this. It has a bunch of loops in it. Of course, if you've written a bunch of these things, you already know that this is not going to be incredibly efficient, but this is a perfectly fine first pass. You run that. Basically, it checks whether something is punctuation. It leaves that out if it's not, and otherwise it splits up and gives you back the words, right? So then you run it and you test it and you see that you got some sort of a unacceptable duration for how long it took to run. If you're going to do this on very, very large documents and millions of documents, this is going to take forever. So you start to think about how you would want to change that. Well, the first thing you probably want to think about is getting rid of this check, right? This for loop for this punctuation check, right? That's more or less clearly going to be taking up a bunch of time. Even without profiling the code, you can kind of see that. Natural thing to do is just substitute as much as possible all of these checks with some sort of regular expression, right? That library is pretty fast in Python. It can solve a lot of your problems if you can translate what you're trying to do with a text with a regular expression match or search function. You run that again, you get something faster. And then you start to profile, right? So you have really amazing profilers in Python, both memory profilers and timing profilers and so on and so on. And so we could run, decorate anything we want with a profile decorator and then run and just see how long it takes, right? So it's pretty clear here we have this lookup on line 62, which is taking the most time, right? So we have that lookup. Okay, so let's try to fix that as the next problem. What's the issue? Well, we're looking something up. Well, what are we looking up? We're looking something that's a string up in a list of strings, right? So maybe that's the problem. Can we do that better? And realistically speaking, yes, we can do that better. If you use a set, right? Set lookup is 01, so that's going to be inherently faster than a list lookup, and that reduces your time significantly, right? So this is not, a developer example. This is just a simplistic example which takes almost no time to do, right? You could arrive from start to finish from your first pass to your later passes within 10, 15 minutes, but it can make a huge difference in your overall process, right? So here's another way to time things, right, in IPython and so on and so on. Okay? And sort of you can convince yourself that you're actually solving the problem correctly by changing the the data structure from a list to a set by doing a simple test, right? So this is by far not, a brilliant code, and this is by far not the best way to optimize this. There are many more things you can do, but this is just a very, very simple process, which we use a lot, and which actually kind of gives back quite a bit as well. So, and also we think quite a bit about data structures, right? The data structure is really bound to what you're trying to do with it, right? There's a lot of convenient data structures out there. Pandas has amazing built-in data structures that allow you for great, statistical manipulation and whatnot. But, for every single task that you have at hand, it makes sense to spend quite a bit of time thinking about what actual data structure you want to use for it, right? Because realistically speaking, you might be just losing a lot of time, right? You might losing a lot of time, you might losing a lot of memory, because the data structure carries a lot of weight with it that you actually don't need for your computations, right? So there's a great post by Salios Lukoeskas, and which I learned quite a bit from, and it's very easy to read and explains very nicely about these things. And a lot of the time, you can simply take your favorite data structure like a Python dictionary and replace it with a simple one that's more lightweight, that does exactly what you want, and takes care of the problem. So, also, as mentioned before, a lot of these tasks, whether it's the data processing tasks or the feature extraction tasks, they're essentially embarrassingly parallel, right? Because everything is independent of everything else, right? So this leads to very, very sort of easy parallelization. Whatever parallelization techniques you know of, apply here, right? And so Python, of course, once again, has really great libraries for this. The multiprocessing library, here's a very, very small example, right, which spins up 4 subprocesses. It's just a few lines of code. There are some issues with this, right? I mean, you have to think about what happens if you're dealing with functions of more than one variable. You can't pickle every function, right? You can't debug as easily, right? If you spin up 4 processes and you try to, it's not possible to actually debug and step through. So what we ended up doing is just writing some pretty simple wrappers for all of this stuff that allow you to just interact with it a little bit easier. So here's a map easy wrapper that Ian wrote, which basically does nothing if your number of jobs is 1. So that allows you to do all your debugging as you usually do it, and then it runs, it spins up a pool as you need, spins up a parallel process as you need it. Right. So this is actually just incredibly convenient. It also allows you to exit with Control-C instead of like having to kill the whole thing. Right. Also, there's a couple of other utilities such as the IMAP easy function in Rosetta, which allows you to send out and return jobs in chunks. Right. It also allows you to debug. There's some Control-C escape issues, but it's but essentially what you're able to do is you're able to take a function, you take an iterable. You say the number of jobs, you say the chunk size, which you can optimize depending on your process, and then you just press go, you debug it when you're setting a number of jobs equal to 1, and after that you just let it go, okay? So all of these things can just be found in Rosetta Parallel. And so what's the sum up? So use irregular expressions whenever you're doing sort of text manipulation, unless you're really certain you're gonna do something better. Use the right data structures. Profile your code to death. We profile it all the time. Multiprocess, because a lot of this stuff is embarrassingly parallel, so that applies. And just note that a number of the Rosetta streamers, they just have a multiprocessing wrapper as part of it. So for example, the text file streamer and the MySQL streamer, say I take the MySQL streamer, I give it the database connection parameters, I give it the query I care about, I give it the results I want to cache along the way, and then I just give it a parameter like n jobs equals to 3 or -1 or whatever, and it will parallelize the task for you. All right, so that's all built in, so you don't have to do that work yourself. Not all the methods are parallelized, right? Some of them don't easily lead to it, or some of them, we couldn't exactly imagine precisely the context for the user, so they're left as is, but the parallelization utility functions can easily wrap whatever you need there as well. Okay, so you can find all of that in streamers. And of course, like everything I just said, I'm talking about Python, I'm talking about Rosetta, but realistically speaking, the framework and the approach applies in pretty much any situation, right? It has nothing to do with Python to begin with, right? I just think it's a powerful and convenient ecosystem to work on. Okay, so I have, Travis, how much time do I have? Does anyone know? I'm over time. Okay, so we're going to skip this. I was just going to say two things. There's, for a lot of the statistical modeling that we do, we end up stepping outside the Python ecosystem. So there's a brilliant library, for example, called Wopal Rabbit, very, very fast for LDA and LSI topic modeling. And we wrote, and our approach there is not to, write wrappers for this library, but just to write converters. So you process your information in Python, it outputs it in the format that the library is interested in. The library, you do something in that library, whatever you run your command line C process, and then you have a Python class which is able to read the output of that, so you can work back in your Python environment, right? So instead of wrapping it with some sort of a sub-process call, all we do is we translate to the format that library is interested in, translate back, and that works pretty well. So there's a bunch of Wopal Rabbit LDA sort of translation functions that are built in, which make life a lot easier, I think, when you're dealing with this sort of stuff. So I'm going to skip that. So here's the summary. So you pay attention to memory, you pay attention to data structures, you profile all the time. Parallelization is really easy here, so do it. And use Python, use Unix, because these are really great for text. And we also write a lot of command line utilities because we think that's a nice way to sort of make this thing much more useful and usable for everyone. So here's a little bit about projects. And so take a look at the library. Please fork it, clone it, use it, contribute. There are many more things that can be done. Thank you.